In this assignment, we're going to look at scatter plots and regression lines, which are two ways to express the relationship between two interval level variables. And actually, regressions can be used to express the relationship between many variables, but we're not going to get into that. We're going to stick to the bivariate or two variable case. To do this, we're going to look at the height of parents and the height of their kids. Now, you already entered your own heights and the heights of your parents into this this form online, and it's a neat part of Google Docs that allows us to collect this data for free and then create a spreadsheet out of it. So when you download the spreadsheet, it looks something like this, right? Each variable is in the columns, and each case is in the rows. So your data would be in one of these rows here. You can see that the data go back to 2011, fall 2011, so we've got a lot of different students from classes going back that far. The timestamp indicates obviously when the survey was done. Where the timestamp is these hash marks, it's just because it's too long to be expressed. Always make it a little bigger and see it like that. You know, if I were to go, make that first column really small, then it's going to make them all disappear. But the number signs, if I expand it out, get rid of all this. Anyway, the rest of these variables are the heights. The first two is the height of the students that you entered in, the height in feet and inches, then feet and inches for mother and feet and inches for father. Okay. Now, the first thing we want to do is we want to have individual variables for height in inches of each student and each of their parents. Right now we have two variables for each of the feet and inches, so we need to create new variables that will combine these data. First thing we need to do is create a data table. So press Control T. As usual, just makes things easier. Yes, my table has headers, okay. Now we're going to create a new variable that's going to be student's height in inches. And as usual, I calculate for the first person, first case, and Excel does the rest. So I'm going to calculate student's height in inches. It's going to be the number of feet they are times 12 plus number of inches, like that. Okay, so I get 70, the first case, that makes sense, and it fills it in for the rest of them. And then I do the same thing for mother's height. Mother's height is going to equal number of feet times 12 plus the number of inches, like that. Okay, and then I do it for father's height. Equals number of feet times 12 plus number of inches, like that. Okay, so you have mother and father and the student, like that. And it runs all the way down. Now you can see that in some cases there are basically these errors because people didn't respond. That's going to create problems, so we want to get rid of them. Now, one way we can handle that is if I sort the data basically in any way, if I just sort it, and I can get all the missing cases at the bottom, okay? Or if I sorted it, if I sorted largest to smallest, it's probably better because I get all basically all this crap where people didn't answer the question at the top, and then I can just highlight the numbers on one side and right click delete, like that. And show that again. Basically I want to get rid of all the missings because it's going to screw up the scatter plot. So again, what I do is I can sort father largest to smallest. I get all these cases where there's nothing there. I can highlight the numbers side and just delete those cases, and I'm left with, should be basically everybody, all the rest of it's non-missing. People actually did answer the question. There's actually one exception. I see for mother. I can get rid of, do the same thing for mother there and delete that one. And again, you know, your data are going to be different because you have collected more data than I have here. So just want to make sure you delete any cases where there's missing data, or else it'll screw up the scatter plot. Okay, so now we have the data set up, ready to go. We now want to create the scatter plot and regression line. And so to do that, first thing is, remember, is when you're creating the scatter plot, is you want the cursor outside the data set. If I have cursor inside this data table, then when I go insert and go to the scatter plot icon like that, I get basically this scatter plot, or I don't know what it looks like, but it's looks like a drip painting or something. It's just Excel tried to throw in all the data at once. It's just garbage. So instead of doing that, you want your cursor outside the data set, so Excel doesn't try to throw everything in at once. Then when you go insert scatter, you get a blank canvas. Now I can add carefully to that blank canvas. Now one thing that I should note is I want to make sure I know the name of my data table and that it's actually named in a reasonable way, so I know what to do. So if I go back to this data, click back anywhere in the data table, click Table Tools. Okay, you might not be able to see this on this. Here we go. Again, Table Tools. Here's the table name right here. I'm going to actually change that. I'm going to call it heights. Okay, you want the table to be named something. It doesn't matter. It's just something that's intuitive and that you'll remember. Because when you're going to enter the names of the variables in the scatter plot, you're going to have to know the name of this table. Okay. Okay, so now I did that. The other thing that I should have done already, I forgot, is I want to look at the relationship between parent's height and student's height, but I have mother and father. I can't throw all of these into the scatter plot. So I need another variable here, actually. I'm going to call it parents. It's basically, it's going to be an average of parents' height. So there's several ways to do this, but the easiest way is you can just use the average function, like that, and average mother's and father's height, like that. Okay, and so we get the average heights for mothers and fathers. And I'm going to use that in the scatter plot. Okay. So go back to the scatter plot and right-click on this blank canvas, basically. Select data. I'm going to add. Now I get edit series. So forget about the name. Doesn't matter. You want to focus on the x values and the y values. What's in the x values? The x values, the x variable is the independent variable. It's the predictor variable. It's what comes first, which is parents, right? Parents' height. So in order to enter that, we have to enter the name of the data table, which is heights, and then in square brackets, the name of the variable, which is parents. As soon as I do that, you can see Excel recognizes it because you see the numbers of that variable. Y variable. The Y variable is student's height. Again, I enter the data table, and then in brackets, the name of the variable, like that. It should tell you, you should know pretty quickly after you enter the names of the variables whether this worked, because it'll highlight it if it recognizes it. Then I press OK, and OK again. Now I'm left with the beginnings of a scatter plot without the annotation details. The The other problem here in this scatter plot is we have all this wasted space. Why is that? Well, first, let's add some axis titles here. Okay, what's in the x-axis? This is the average parent's height. That's the x. What's in the y? The y is student's height. Or we could just say offspring height. Okay, like that. And then what's a title? Well, a standard title for a scatter plot is just y variable by x variable. So this is offspring height by the average parent's height, like that. Okay. Now we can see that clearly there's no parents whose average height is below like 60. Okay. And there's no offspring's height that is lower than like 55. So all of this space here is wasted because we don't have people who are the size of action figures. So what we want to do is we want to modify the minimums here. So if I click on this horizontal axis, format the axis, change the minimum from 0, here I'm going to say 60. Okay. That spreads things out. Do the same thing, just click on the y-axis, right click, format. Instead of 0 minimum, I'm going to say 50, okay? Like that. Actually, you know what, 55. Do that. Doesn't matter exactly what it is. What matters more is just to make it so that the points are spread out across the chart and there's not a lot of wasted space. So, what do we have here, aside from someone whose parents are freakishly tall, relative to everyone else, anyway? What we have here is points that tend to go up and to the right, as we would expect, of course. People whose parents are taller tend to be taller themselves. So we have, when parents who are taller over here, so say this person here, they tend to have taller children. Okay, but there's still a bunch of points. It's a little bit busy, not a lot of information. So we want something that's a little bit simpler, more straightforward to deal with, less information, data reduction. So we'll do that with a regression line, which is a summary of this scatter plot. So what I'm going to do is I'm going to add trend line. Get more options. It's going to be a linear trend line, what means linear in the sense that it's going up at a steady rate. Okay, you can see some of these other options where it goes up at a very fast rate and then it slows down, or a very slow rate and then speeds up, or goes up and down, whatever. We're going to say a simple linear trend, and we're also going to display the equation on the chart. The line and the equation go together. This is called a regression line, and this is called a regression equation. It's a bivariate linear regression and regression equation because bivariate in that there's only two variables. It's actually possible to have many variables on the right-hand side of the equation. We only have one, and there's y, so it's bivariate, two variables. Linear because, again, it's going up at a constant rate. What else about this regression equation? In other words, how do we make sense of it? Okay. The regression equation is in the same format as standard equation for a straight line, which you learned probably a long time ago in school. Y equals mx plus b. Y equals mx plus b. If that rings any bells, even if it doesn't, unlike in school where sometimes people learn that equation independent of actually any kind of real life application, but in this case it does have real life application. You can use it to predict things. In this case, use it to predict offspring height by the height of their parents. You have the height of their parents, and they take the average, you can predict the height of the kids if you have enough data, right? In this case, y equals mx plus b. Y is what? Y is the predicted value of offspring height, okay? Y equals mx plus b. M is this number before the x, which is 0.7432. What is m? M is the slope. Okay? What is the slope? The slope is the expected change in y for every unit change in x. What that means in this case is for each additional inch of average parent's height, or to make it simpler, for each additional inch of parent's height, we expect offspring height to go up by 0.74 inches. Okay? What is x in this equation? X is the average of parent's height. That's what's in the x-axis. And then what's this other number? 17.807. Well, that's the b in the y equals mx plus b. That's the y-intercept. The y-intercept is the value predicted for y when x is equal to 0. Because if x is equal to 0, this cancels out, and you're left with just 17.807. Okay? That's it. Okay, so to go through this again, I'm just going to create a new sheet here. Sometimes people get confused. The standard bivariate regression y equals formula is y equals mx plus b. Okay? In this equation, y is the predicted value of the variable in the y-axis. Okay? M is the slope, which is the expected change in y for every unit change in x. Make this a little longer. X is the value of variable in the x-axis. And b is the y-intercept. Okay? So these are the four parts of the regression equation that you should know. If we go back to this regression equation, now we're going to translate these general parts of the regression equation into what specifically they are in this case. What is y in this regression equation? In this case, it is the predicted value of offspring height, or I can just say predicted offspring, predicted height of offspring. Okay. What is m? M is 0.7432, right? Which is, again, the expected change in y for every unit change in x, or in this case, we would say, make this in the English a bit, for each additional inch parent's height, we predict student's height, or offspring height, I should say, to increase by 0.7432. Okay? Like that. X is simply average of parent's height. Right? And B is the 17.807. Right, that last number there. And what is that? This is the value predicted for y when x is equal to 0. Because, again, in this equation, if x is 0, the first term cancels out. This is 0. And you're left with this, 17.807. Now, in this case, it doesn't have a substantive interpretation because you can't have parents with an average height of 0, right? So it doesn't make sense, but it's still part of the equation. In some cases, it does actually have a substantive interpretation if it makes sense if x is equal to 0. Okay, we'll see that in the used cars example because you have the x variable in that case is age. So an age of 0 would be a new car. But in this case, it doesn't make sense. Okay, so that provides you an overview of what this regression equation means. You can see each of these points here represents a person, right? So you are represented as one of these points here. So just to get a sense of the way this works, right? So let's take this person here. Okay, the person represented by this dot, that point right here. The average of their parents' height was 62 inches, and they were perhaps 57 or so. Okay, 57 inches. You could probably, find yourself on the graph if you wanted to. This person had parents who were extremely tall. At least one parent who was extremely tall, like 78.5 inches, but they weren't that particularly tall. They were 65 inches tall, right? So that leads us to think about where the points are in relation to the line, right? If somebody's right on the line or really close, then what that means is that the prediction provided by the regression equation is pretty accurate for that person, or it's just predicted precisely. Most people, though, aren't right on the line. In fact, a lot of them are far away from the line. People who are, say, much lower than the line, below the line, those are people who are shorter than we would predict based on how tall their parents were. People who are above the line, the points above the line, are people who are taller than we would predict based on their parents' height. Okay? That's the idea. So if you're able to find yourself on here, you can then get a sense, are you taller than you would expect based on your parents' height, or shorter, or about what you would expect? That's one thing you can sort of learn here from this. Another thing to note going forward is the distance between the regression line and the point, or where you are, or where any person is. It's called the residual. Okay? And the residual tells you, it's the difference between what we would predict, what the regression predicts, and what's in actuality the case, right? And we'll get into that more as the assignments go forward. Another thing to note is, we talk about this as a regression line, and sometimes people ask why is it called a regression line? What does that mean? Regression is like going back, right? Regress is to go back. Well, actually, one of the first uses of regression was to do exactly what we're doing here. To look at, and this is basically where regression got its name, to look at offspring height by parents' height. The idea here is, say if you have parents who are extremely tall or extremely short, what ends up happening to the kids of those people? The kids of extremely tall parents tend to be taller than average, and the kids of extremely short parents also tend to be shorter than average. Okay, but what also happens is there's what's called a regression to the mean, and this is where regression gets its name. That if somebody's extremely tall, their kid is likely to be also tall, but not quite as tall as they are. So they're falling back to the mean. And likewise, if a parent is extremely short, their children tend to also be short, but not quite as short as they are. They tend to be closer to the mean than their parents. If this wasn't the case, then you basically end up with something crazy like 30-foot tall people and people who are the size of action figures. That doesn't make any sense. So what we're describing here is something that's a natural phenomenon that has to be the case, where it's not like extremely tall people just keep getting taller and taller as generations go on in their family. What happens is people regress towards the mean. And this is a phenomenon that you can see in many cases. Is not just about height across generations. You can see it in your own test scores. Say, if you get a really bad test grade one time that's well below the average test grade that you're used to getting, chances are your next grade is going to be better, right, than that. And on the other hand, if you, say, happen to get a perfect grade on a test in a class that you're not accustomed to getting that kind of grade, then next time chances are you're not going to have the same luck. And so your grade is going to be somewhat worse. Basically, this is about the luck of the draw and the fact that, whenever you see somebody getting extremely lucky or extremely on the extreme end of some distribution, the next number in the sequence is probably going to be less extreme, and that's where regression gets its name, and that's why regression works particularly well in this case. Is particularly descriptive in this case. You can see that in the slope, right? So for each additional inch of parent's height, offspring height goes up by 0.74 inches. Note that that number is less than 1. The slope here is less than 1. It has to be less than 1, right? If you had the offspring increasing by more than 1 inch for every inch of parent's height, then you wouldn't have regression. You would have the taller parents, the kids of the taller parents getting taller, even taller than their parents. Okay, and the shorter kids, the kids of the shorter parents getting even shorter than their parents. But what you see here with the slope of less than 1 is a case where there's regression to the mean, where the offspring of the tall parents are taller, yes, but not quite as tall, right? And similarly, the offspring of the shorter parents tend to be shorter, but not quite as short, and that's the idea.